Another day, another topics. Science and Technology. Class 10. Scientific Study. 1.2 Fundamental and Derived Units. Fundamental units are the basic units of measurement that cannot be expressed or independent in terms of other units, have their own identity. These units are used to define and measure physical quantities such as length, mass, time, electric current, temperature, amount of substance, and luminous intensity. The International System of Units, SI, recognizes 7 fundamental units. Meter, M, for length. Kilogram, kg, for mass. Second, S, for time. Ampere, A, for electric current. Kelvin, K, for temperature. Mole, mole, for amount of substance. Candela, CD, for luminous intensity. Derived units are formed by combining 2 or more fundamental units, don't have their own identity. These units are used to measure other physical quantities that are not fundamental but are derived from the fundamental units. For example, area, square meter, derived by multiplying length, m, by length, m. Volume, cubic meter, derived by multiplying length, m, by length, m, by length, m. Velocity, meter per second, derived by dividing length, m, by time, s. Force, Newton, N, derived by multiplying mass, kg, by acceleration, m/s squared. Energy, joule, J, derived by multiplying force, N, by distance, m. Power, watt, W, derived by dividing energy, J, by time, S. Pressure, Pascal, Pa, derived by dividing force, N, by area, square meter. The fundamental units involved in the derived unit. The fundamental units involved in a derived unit depend on the combination of base units used to define that unit. For example, the formula of speed is V equals S/T and units combine as meter, m per second, s. Derived unit of speed is meters per second, meter per second, which involves the fundamental units of length, meter, and time, second. Similarly, the formula of force F equals ma. The derived unit of force is Newton, N, where N equals kgm/s2, which involves the fundamental units of mass, kilogram, length, meter, and time, second. Units analysis of equations. Unit analysis, also known as dimensional analysis, is a technique used in physics and engineering to check the dimensional consistency of an equation. The study of the relationship between physical quantities with the help of dimensions and units of measurement is termed dimensional analysis. Using dimensional analysis to check the correctness of physical equation. Let's say that you don't remember whether time equals speed/distance or time equals distance/speed. We can check this by making the dimensions on each side of the equations match. Reducing both the equations to its fundamental units on each side of the equation, we get. However, it should be kept in mind that dimensional analysis cannot help you determine any dimensionless constants in the equation. Homogeneity principle of dimensional analysis. Principle of homogeneity states that dimensions of each of the terms of a dimensional equation on both sides should be the same. This principle is helpful because it helps us convert the units from one form to another. To better understand the principle, let us consider the following example. Example 1. Check the correctness of physical equation S equals at plus half at 2. In the equation, S is the displacement, U is the initial velocity, V is the final velocity, A is the acceleration and T is the time in which change occurs. Solution. We know that LHS equals S and RHS equals at plus 1/2 at 2. The dimensional formula for the LHS can be written as S equals L1m0T0 1. We know that RHS is at plus half at 2. Simplifying, we can write RHS as UT plus A T2 L1m0T1 L0m0T1 plus L1m0T2 L0m0T2 equals L1m0T0 2. From 1 and 2, we have LHS equals RHS. Hence, by the principle of homogeneity, the given equation is dimensionally correct. Applications of dimensional analysis. We make use of dimensional analysis for three prominent reasons: to check the consistency of a physical equation, to derive the relation between physical quantities in physical phenomena, to change units from one system to another, unit conversion, to derive formulas. QN discuss the importance of unit analysis in scientific calculations and problem solving. Limitations of dimensional analysis. Some limitations of dimensional analysis are: it doesn't give information about the dimensional constant. The formula containing trigonometric function, exponential functions, logarithmic function, etc. cannot be derived. Cannot determine dimensionless constants. It gives no information about whether a physical quantity is a scalar or vector. Possible questions: if the speed of an object is measured in meters per second, meter per second, what are the fundamental units involved in this derived unit? Given the equation F equals ma, where F represents force, m represents mass, and A represents acceleration, analyze the units involved in the equation and identify its correctness. How can unit analysis help identify errors or inconsistencies in equations or measurements? F-unit analysis, also known as dimensional analysis, helps identify errors or inconsistencies in equations or measurements by examining the units of measurement involved. It ensures dimensional consistency in equations, detects incorrect conversions, validates derived equations, identifies missing or extra terms, and ensures proper interpretation of measurements. By carefully analyzing units, unit analysis can reveal inconsistencies, allowing researchers to rectify errors and improve the validity and reliability of their work. QN check the correctness of the physical equation V2 equals U2 plus 2S2. F. The computations made on the LHS and RHS are as follows. LHS V2 equals V2 equals M1S12 equals M2T2 1. RHS U2 plus 2S2. Hence, RHS equals U2 plus 2S2. RHS equals M1S12 plus M1S2 M12. RHS equals M2S2 plus M1S2 M2. RHS equals M2S2 plus M1S2 M2. RHS equals M2S2 plus M2 2. From 1 and 2, we have LHS does not equal RHS. Hence, by the principle of homogeneity, the equation is not dimensionally correct. Thanks for watching.